Swayam Prabha. Digital India. Educated India.
We will continue with our discussion on the quest for getting IB lambda, or the I of a black body, where I is the intensity. So I told you different people were trying to work out. So some of them use thermodynamic principles, right? Like they said that radiation has a pressure, radiation can be treated like a gas which occupies a volume, which exerts a pressure and so on. Therefore they related the radiation pressure, or they related the radiation pressure to the intensity. That was the first part of the story. The second part was in the last class we looked at the definition of radiation energy density U, right, and we related the radiation energy density to the intensity, right. So what we have seen thus far is there is intensity, so there is a radiation pressure, so we related both the radiation energy density and the pressure to the intensity I, right. So in the last class some of you may not have understood the whole thing fully, but it's but the mathematics should not really cloud the physics. The basic idea is first Bartoli proposed a thought experiment wherein he proposed a hypothetical cycle. That is a thought experiment. A thought experiment is something which need not be done in the laboratory, but based on established laws you can, for example, you run a thermodynamic cycle. If it is taken from A to B, from B to C, again from C to A, and if all the processes satisfy the laws of thermodynamics, then the cycle must also satisfy the law of thermodynamics, and then you can derive certain things without doing the experiment. Just like you are doing some computer simulation, without actually doing the experiment you find out what will be the drag coefficient. You do a model, a scale model of an automobile and put it in a numerical wind tunnel and do your, that is fluent, do your fluent calculations, find out what is the CD, the coefficient of drag. It is something like this. So taking a cue from Bartoli's thought experiment, then using our knowledge of thermodynamics, then we got a relationship between the intensity and we defined the radiation pressure in terms of the intensity. Please remember that for both radiation pressure as well as radiation energy density, we derived expressions for both these by what? By looking at radiation which is incident on a surface, okay, which is looking at by looking at radiation which is incident on a surface. So radiation pressure we got it as 4 pi IB by good 4 pi, okay. What is this? Shall we start from 1 or this was 6, okay, we will continue with 6, okay. We also saw that UB was 4 pi IB by C, this was 12, 13. So looking at 6 and 13, or simply all right. Now what is the relationship between what is the relationship between the intensity and the temperature T? suppose it is integrated for all the wavelengths and it is integrated over the hemisphere, and if it is a black body, we know that there is a relationship between I and E. What is that? E equals pi IB. Therefore, if you get a relationship between I and T, it is as good as getting a relationship between E and T, and you already know what the story is. E is sigma T to the power of 4, that has also been independently confirmed by experiments. Whoever has done an experiment, they have found out that if the emissive power from a black body is proportional to T to the power of 4, okay, and then if you plot E versus ln T, or right, ln T versus ln E versus ln of sigma T to the power of 4, you can find out the intercept and get the constant and all that. But now from thermodynamic arguments, can we get the same thing? That is the story. Now consider radiation to be a gas. Occupying a volume V with pressure P at a temperature T and all that, right. Now we will start the story like this. So U correct, the total internal energy is the product of the specific internal energy multiplied by the volume. The specific internal energy, I am free to define the specific internal energy as energy per volume or energy per mass. In this case I have defined it as energy per volume. Energy per volume into volume will give you joules or kilojoules or whatever. Okay. Now if radiation is a gas, all your Maxwell's relations, all your TDS relations have to be valid, okay. Therefore TDS is du okay. You can put the numbers. I am expanding U as U into V, right. What is the relationship between P and U? But P equal to U by 3. Therefore okay. Therefore TDS equal to what is it? V du O by 3 Q dV, good. I can divide by T throughout, okay. Okay. So what is the story now? Radiation is a gas, so we exploited the TDS relations. We also exploited the definition of internal energy is the product of specific internal energy into V. We did UV is equal to UdV plus VdV, all that. Now I have come to a critical stage. I am almost there. I have to come out with an important step. From whatever knowledge you already have, nothing new, nothing great, no quantum mechanics, nothing, simple thermodynamics. S is entropy. Is entropy a path function or a point function? So therefore entropy is a point function, therefore ds is an exact differential, okay. ds is an entropy, so S is a property. So therefore dou by is it correct or it should be the other way? Huh?
It should be related to u and v, sir. S is a function of u and v. So
No, u is a function only of t. I want it only as a function of t and I want it only as a function of v and t. What do you want to do now? It looks better now? Now it looks better? Otherwise we will get stuck somewhere. Now what is the story? Huh? Dou by dou v of v by t. So I keep telling you thermodynamics is a very slippery subject. If you are not on your feet it will let you down, okay. Du by dt, okay, is equal to I know that I am on track, okay. How many of you did not understand this step? If z is a function of x y, you can write that dz is equal to m dx plus n dy, right. So dou m by, is it correct? Did I make any mistake? It's fine. We are exploiting the property of an exact differential. We have done that, right? We have done that in our ME 1100 introduction, I mean the basic thermodynamics course. Okay. Now we have to put some. Now you can do this, you don't have to wait for me. Yeah, left side dou by dou v of what do you do? Huh? So we will just say 1 by t correct is equal to minus 4u by 3t square, correct. D by dt, first term is 4 by 3 t, 4 by 3t du by dt, is that correct? Fine, okay. Now are there similar terms? This fellow can be brought to this side and this fellow can be brought to this side, therefore 4 by 3 we call it as 23 3 goes. Yeah, you can integrating both sides. Ln u equal to 4 ln t, correct, plus some C1 or A1 whatever. Oh, I will put C1, okay. U is some C2, some constant. Alright. Now this is equation number 25, but U is equal to, in terms of 4 pi
IB by C.
I don't like C2 is bad, I don't like, I make it A, no, it's more fundamental. So 4 pi B by C equal to A, alright. Huh? Wait, AC by 4 pi, okay. For a black body, okay, it is diffuse and after the integration of the hemisphere is done, okay, therefore equation 28 is a very important, equation 28 is a very important relationship which was figured out in the last part of the 19th century, okay. Stefan and Boltzmann independently, Stefan and Boltzmann arrived at this, okay, and then they matched the experimental data. From theory you know that EB is AC by 4 into T to the power of 4, C is velocity of light in vacuum 2.998 into 10 to the power of 8 meters per second, velocity of radiation. However, A is not known. So if you have to get the value of A, you have to match this expression with experiments which have been done, and by matching it with the experiments it is now known that AC by 4 is 5.67 into 10 to the power of minus 8. That is why it is called the Stefan-Boltzmann's law. Now you understood in life how the T equal to sigma T to the power of 4, but still we do not know what the I is, notwithstanding the fact that we are ignorant about I. Based on thermodynamics we are able to get E, okay. Thermodynamics is able to take you up to a certain level, right. Now it is now known that so now everything falls in place. There was some Bartoli figured out that something is called radiation pressure, people figured out how to define the radiation pressure in terms of intensity, how to introduce a radiation energy density, and exploiting the laws of thermodynamics, how we can work with a powerful tool, okay, which we have, that is thermodynamics. Some people said if all knowledge is completely wiped out, the world you remove, we burn all the books, you burn all CDs, you burn all flash drives, you burn all data centers, but only one thermodynamics book is there, you can rebuild the whole thing with thermodynamics. So that is a power. I am not saying because we are all mechanical engineers, but okay, thermodynamics is the queen of sciences. Okay, so it is now known maybe mathematics, but the theoretical physics will say physics, theoretical physics, whatever. It is now known that watt per meter square Kelvin power. You can use a mnemonic 5678, 5678, but put -8. Okay, you have to use -8 and T must be in Kelvin. Okay, otherwise you will be violating Prevost's law. Any body at a temperature of 0 degree centigrade will not emit radiation. Okay, that violates Prevost's law. Therefore, this is called sigma. That okay, sigma is called the Stefan-Boltzmann constant. In honor of the two scientists or two physicists who figured this out. Okay, there is a Stefan-Boltzmann constant. Okay, so Joseph Stefan (1835 to 1896), I guess. Then Ludwig Boltzmann, these were the two physicists. Joseph Stefan was Austrian, Boltzmann was a German. Stefan was the PhD guide and Boltzmann was the student. Boltzmann did PhD with Stefan. He got his PhD at the age of 22. He got PhD at the age of 22, and at the age of 25 he was appointed full professor of mathematical physics at the University of Graz, Graz, GRA. At the age of 25 was appointed full professor. Okay, and Boltzmann did so much of work. Okay, so Boltzmann and but Boltzmann was a professor in Germany. Stefan was basically Austrian, but Austria's people who have been to Germany and Austria, you know that Austria is more or less Germany, so they speak only German and all that. So right, so this is the story of this Stefan-Boltzmann's law, but we still don't know what the I is. Okay, but we have achieved a certain kind of this thing has come where you know that the black body radiation power is proportional to T to the power of 4. Okay, fine. So it is just from basic thermodynamics they established T to the power of 4, they did experiments, they matched the experiments with the theory and got the sigma. So that PhD was so easy. Okay, but at those times when you imagine 150 years back when people didn't know anything at all, it was something radical, isn't it? They didn't know something could be raised to T to the power of 4 because conduction is dt by dx, convection is HA delta T, radiation alone is some T to the power of 4. Okay, so Stefan is not there in Germany. Stefan, they always say Stefan. Now, so many questions are still unanswered. For a given temperature, how does this IB vary with lambda? For a given temperature, how does IB vary with lambda? Right? Does it hit a peak? Are there multiple peaks? And for a given wavelength, how does IB vary with temperature? Okay, and what happens when lambda tends to 0? What happens when lambda tends to infinity? Okay, what is that IB lambda which will satisfy all this, which we are able to intuitively feel or guess? Are you getting the point? Therefore, people started working out this candidate blackbody distribution. But please remember that any candidate blackbody distribution has not only to satisfy whatever we have considered so far, it should also satisfy integral lambda is equal to 0 to infinity, integral theta equal to 0 to pi by 2, integral phi is equal to 0 to 2 pi, ib lambda cos theta sin theta d phi d lambda equal to sigma t to the power of 4. So, it is actually an inverse problem. What is that IB lambda which will satisfy all this? Okay. So, people, the best brains, in the last part of the 19th century and the early part of the 20th century worked on this problem. It was an unsolved problem in physics. Okay. So, we can call this as candidate blackbody distribution functions. What are the various candidates? On his tomb, Boltzmann, S is equal to K ln omega is there written, that is one expression is enough, that epitomizes his lifetime work. Okay, E equal to mc square, that is it, all his life. So, that is the essence of his work, right. Okay. So, everybody strives to reach this thing, but it is only nature abhors singularity, right. I mean, yes, whatever. So, nature does not prefer geniuses, so we do not have to worry, okay. It does not have to be us. But everybody has a role to play, we will do our work, that is all. It may happen that sometimes something will click, or we may die without something clicking also, okay. But so long as our existence is justified, it is okay. There is no need to worry something like, do something like Prandtl, or it may come, it may not come, okay. But if you say I want to do something like that, it is okay, but I do not know when, there may be some intuitive flash of insight, that alone is not enough. So, you have to be in the right place at the right time, okay. So, and then it requires years of hard work, right. So, though these people have done all this work in the 20s and 30s, Nobel Prize is not awarded for upstarts. At the age of 65, when you are 65 or 70, they will award the Nobel Prize for what you did 30 years back. Nowadays, those days they got the Nobel Prize when they were very young. Even Feynman got when he was 47 or 48, right. But nowadays it is becoming very difficult, okay. Fine. So, candidate blackbody distribution function, okay. What is that IB lambda? That satisfies the following. IB lambda tends to 0 as lambda tends to 0, right. Again, otherwise it will become a singularity. If it tends to infinity, it will become a singularity, isn't it. By the same token, IB lambda must become 0 as lambda tends to infinity. Otherwise, everybody will build sophisticated devices which will emit radiation only at very low wavelengths, and RG all the other wavelengths, and then, but that is not going to work. So, at both ends of the spectrum, it has to be 0. I think we have to continue with our numbers. Shall we put it as an equation? We will just leave it, no? Okay. So, IB lambda is equal to 0 when t tends to 0, correct? So, at absolute 0, no radiation possible. By the same token, IB lambda tends to infinity as t tends to infinity, right? Furthermore, for a given temperature, right? For a given temperature it has to satisfy. What? Huh? Oh yeah, correct. Yeah. Now the best brain started working on this. It's a kind of an inverse problem. Okay, there are asymptotic limits, lambda tending to 0, lambda tending to infinity, t tending to 0, t tending to infinity, and then the integral has to be equal to sigma t to the power of 4. So who is the first guy in this? Wien. Okay. So Wien was the first guy to come out with a distribution. Okay. So Wilhelm, Karl, Werner, Otto, Fritz, Franz, Willy, Wien. Okay. So Wilhelm, Karl, Werner, Otto, Fritz, Franz, Willy, Wien, 1864 to what happened? Okay. Wien. Needless to say, he is also a German. He is also a German. Okay. The name is so crazy that automatically. So, needless to say, radiation fully, everybody is, all these characters are all mostly Germans. Okay. So, it's only after the Second World War the story changed, right. So, all of them were from Central Europe. Okay. So, in the continental Europe, but somewhere there in outside the continent, I mean that part of Europe which is not considered continental Europe is the United Kingdom, right. Normally when you say continental Europe, we do not include UK, right. Now, he proposed in 1896, he proposed is IB lambda W. IB lambda W means IB lambda proposed by Wien. Okay. So this is basically C1 this was Wien's distribution. So where C1 and C2 are the two radiation constants. Is given by 1.19 10 to the power of 8 watts micrometer per 4 per meter square. Okay. C2 is the second radiation constant. Fourteen 1438 micrometer Kelvin. What happened? No, I am not telling you whether it is correct or we will examine it now. He proposed it. If it satisfies everything, then Planck, there is no role for Planck. Okay. So what is the problem with this fellow? T tends to infinity. Okay, suppose consider this. It is okay for short wavelengths. See, basically people did the experiments. They found out IB lambda versus lambda for various t's, and it is already there. Now there must be a theory which satisfies this. That theory must satisfy all these asymptotes, and also the integral must come to sigma t to the power of 4. So all the physicists are trying to work in their respective laboratories, trying to figure out an IB lambda. Each of these physicists claim that his IB lambda is the correct distribution for characterizing blackbody behavior. The basic problem with all these expressions is all of these fellows try to explain these with thermodynamics or classical physics or kinetic theory of gases. but they didn't know that using classical physics black body behavior can be explained because it will cup. So Planck introduced that E is equal to h nu and it has to be in multiples of 1 h nu, 2 h nu, that nobody thought of. It was too futuristic at that point in time. So they were all trying to, they felt that with the physics and classical physics and thermodynamics which has been developed, enough knowledge is available to explain black body behavior. Okay, so they faced their Waterloo because of this approach. Okay, now what is the problem with this? As t tends to infinity, IB lambda V, when t tends to infinity this becomes 0, denominator becomes e to the power of 0, therefore it tends to a finite value. Okay, IB lambda tends to a finite value, which is not correct, because you know that as the temperature increases the molecular agitation will increase so much, the body will radiate more and more, and experiments do not suggest this. Therefore the Wien's distribution is valid only for certain part of the spectrum. Okay, so for example we can write like this, we can draw so IB lambda and 6000 Kelvin, so 10 to the power of 5, 6, 7, IB lambda watts per meter square, micrometer steradian, good. And what will be this? I am looking at a spectral distribution, x axis must be lambda in micrometer, good. So we are always looking at micrometer, so we let us say 0, 0.5, 1, 1.5, 2. Okay, so it's not very clear, right? So which will be a better color? So this experiments or Planck I can say. Right now we do not know because we have not seen the Planck distribution. This is Wien. So there is a significant departure from the experimental values at higher values of the wavelength. So this is for a representative temperature of 6000 Kelvin. Why are we so hung up on 6000 Kelvin? 6000 Kelvin is an important temperature for engineering because sun, okay, it is an important thing for us. Therefore if you take the spectral distribution of IB lambda versus lambda corresponding to a black body at 6000 Kelvin, the Wien's distribution significantly departs beyond the peak corresponding to the 6000 Kelvin. Okay, left side of the spectrum the story is fine, so it is agreeing with the experiment. So and it is based on, it is semi empirical and it is based on thermodynamics, and he didn't look at the experimental results available in literature, he didn't see. That is why in his paper in his papers he has not bothered to rationalize or explain what are the reasons for the departure from observed experimental. He proposed on his own independently without looking at other people's papers or other people's published experiments, because the Stefan and Boltzmann already have done some experiments and they did all that, right, and then other people have also measured IB lambda, right. So this is the first distribution. Now come two other scientists, Rayleigh and Jeans. So Lord Rayleigh and Sir Jeans, so 1842 to 1919, and he is 1877. In 1900 Lord Rayleigh and 1905, Sir Jeans independently worked out, Lord Rayleigh in 1900 and Sir Jeans in 1905 independently worked out yet another incorrect distribution for IB lambda. Okay, what was that distribution? IB lambda of Rj equals yeah. Now please look at the difference between the Wien's distribution and Rayleigh-Jeans distribution. Numerator is the same, C1 and C2, the first C1 is called the first radiation constant, C2 is called the second radiation constant, the two radiation constants are the same, numerator is the same, denominator there is a departure. These fellows are saying C2 by lambda T, this guy said it is e to the power of C2 by lambda T. Okay. So what happened was the Rayleigh distribution, Rayleigh-Jeans distribution goes like this at 6000 Kelvin. So this goes as lambda to the power of minus lambda to the power of minus 4. At shorter and shorter wavelengths, what happens to IB lambda? It goes to infinity, but that was not observed by anybody. So that means I can have very small wavelengths and I can produce terrific IB lambda, which is far from the truth. Okay, and Lord Rayleigh and Sir Jeans were the highly respected scientists in those times. They were celebrated physicists. So their distribution miserably failed for very low wavelengths, and with respect to wavelength below visible we call it as ultraviolet. I mean the notation is counterintuitive, but it is ultraviolet, the terminology is with respect to the frequency. So when you are approaching the ultraviolet radiation, then there is it is shooting up, which is deviating significantly from the observed experimental data. Therefore this dramatic failure of classical physics, which was in the hands of two greatest physicists, was called as the ultraviolet catastrophe. Okay, so this was a shame for classical physics. Okay, but the beauty is in 1901 Max Planck gave he just added one minus 1 and it this is sheer RG, no, this is absolute RG. Okay, he just added on minus 1, okay, and then his distribution agreed beautifully well. It was showing excellent agreement with the IB lambda distribution. So whether you consider any temperature, for any temperature at all wavelengths, it gave very good agreement. Then he started seriously thinking, why is it giving agreement? How do we put minus 1? What is it? So first he did only curve fitting. Okay, sometimes you do reverse engineering, right? First you draw the curve and then you put the points. Okay, but he didn't do that, but he essentially did curve fitting. So see, both fellows are very close. See, Wien, he was e to the power of C2 by lambda T, this fellow just put minus 1. Okay, now it gave excellent agreement. Now Max Planck gave in 1901, but this fellow in 1905 he gave the incorrect distribution. Both were published in the same journal called Philosophy Magazine. So either the editor or the reviewer has not seen, this fellow has not seen his paper, and he, as far as Planck is concerned, he got excellent agreement with this. Therefore this fellow should know that I am not getting agreement, I am having ultraviolet catastrophe, because the editors were very close to these two guys. So they just allowed these papers. So you can see that this is the troubled birth of quantum mechanics, because they were respected scientists, it should be correct. So they, 4 years after the correct result was published, Sir Jeans published the incorrect result of okay. So this is the, so some in order to understand the science perfectly you have to understand its history, that is what Auguste Comte has said. So you have to understand this, so that is why I put the history in perspective. Now you know that there is a lot of controversy surrounding this. In tomorrow's class, first we will derive the incorrect distribution IB lambda of Rayleigh jeans, how he, from wave equation he figured that incorrect distribution, and how Planck proposed the quantum hypothesis. Okay. So I hope to finish it in the next 2 classes or max 3 classes. Then once you have this IB lambda, you can do all, you can do whatever you want. Differentiate IB lambda with respect to, you can differentiate with respect to lambda and then find out where it is hitting maximum. You can integrate, it will become sigma t to the power of 4, all those things are possible. Okay. But right now there is no quantum mechanics. First it started with curve fitting. We put -1, it is agreeing. Now how is it possible for me to put -1? -1 will never come if you use classical physics. Therefore Planck figured out that unless he uses E is equal to h nu, he will not get this result. Therefore E is equal to h nu must be correct. If E is equal to h nu, then the continuous transfer of energy is not possible, energy is transferred only in steps of h nu. Therefore there is a quantum jump, 1 h nu, 2 h nu, and therefore h cannot be infinitesimally small, h cannot be 0, h has to be a finite constant. That constant is 6.627 in 10 to the power of -34 joules second, it is now called as the Planck's constant. His major contribution was first curve fitting, then second proving that h is not 0. That not 0 means it cannot be infinitesimally small, it has a finite value, and you can have 1 h nu, 2 h nu, 3 h nu, you can't have 1.3465 h nu to 1.3467 h nu, energy transfer cannot take place. As of today it is the correct distribution because it satisfies all your asymptotic relationships, it also agrees well with the experiments. We do not know what will happen in the future. Okay, fine. So we will stop here.